We've been increasing the complexity throughout the last few chapters. We'll increase the complexity one more time by introducing multivariate analysis of variance.
We'll now increase the complexity, beginning with the t-test. Notice the t-test had one independent variable with two levels, here control and experimental. We increased the complexity a bit when we went to analysis of variance. Here a one-way analysis of variance with a single independent variable, but with three levels of the independent variable. We increased the complexity a bit more when we went to a two-way analysis of variance. Here we have two independent variables, gender with two levels, and experimental condition with three levels. But in each case, each of these models involved a single dependent variable. We're now going to increase the complexity and have analyses that involve more than one dependent variable. We're going to conduct a multivariate analysis of variance, a MANOVA. It's multivariate in the sense that there is more than a single dependent variable. Multivariate analysis of variance, or MANOVA, is used to analyze designs when you have more than one dependent variable.
So you see the M in front means MANOVA, and it means multivariate ANOVAs. We're going to do a one-way MANOVA where we'll have three levels of the independent variable: control, experiment 1, experiment 2.
That's similar to what we've seen before, but the complexity we're going to add is now illustrated here. Rather than having a single dependent variable, we have three dependent variables. So we're going to look at this package of three dependent variables and see if that package of variables differs across the levels of the independent variable. Since we have three dependent variables, the null and alternative hypotheses look a bit different than before, but yet are quite similar.
Here's a picture of the null hypothesis. There will be no significant difference between the package of dependent variables, and the alternative hypothesis says that there will be differences.
That at least one of those variables or one of those groups differs in some way that could not be attributed to chance. We now talk briefly about test statistics. We did a t-test, and we tested the difference between independent and dependent t-tests with a t-ratio. When we did analysis of variance, the test statistic was the f-ratio. When we move to MANOVA, there is more than one test statistic to test this null hypothesis. There are 4 MANOVA test statistics printed with each SPSS analysis. They're Palais' trace, Wilks' lambda, Hotelling's trace, and Roy's largest root. The most widely used, the most often seen test statistic that's interpreted is that of Wilks' lambda. In our example, which we'll show you briefly on how to run a MANOVA on SPSS, we'll interpret Wilks' lambda. The next video actually illustrates how to conduct a MANOVA with SPSS.